Okay, so we are now going to look at some examples involving the natural log. So Eg14. Differentiate y equals 3 ln x. Well, this is just a standard differentiation. There's no product, there's no embedded function. It's just the same as if it was 3x or 3p. So it'll be 3, and then when we differentiate ln, we get 1 over. So it'll just be 3 over x. B. This one, embedded function. I can differentiate that, and it's tucked inside this natural log function, so I have to deal with it separately. So this is a chain rule. So cover the embedded function, differentiate ln finger, you get 1 over finger. 1 over finger is 1 over x squared plus 1. And you have to multiply that by the differential of what you covered up, which is going to be 2x. So dy dx will be 2x over x squared plus 1. C. So here we've got a product, we've got the x squared multiplied by the natural log function. So this is going to be product rule. So we let u be the first part of the product, v be the second, differentiate u, we get 2x. Here we've got an embedded function, so we've got a chain rule here. dv dx, cover up the embedded function, so 1 over finger times what you covered up, differentiated, which is 4. So that's going to be, the 4 is going to cancel, 1 over x. So the product rule, dy dx u dv dx plus v du dx. So u is x squared times dv dx 1 over x plus v times 2x. Ooh, nearly dropped off the screen there. So the x's will cancel, and you've got x plus 2x natural log of 4x. Take an x as a common factor, 1 plus 2 ln of 4x. So that's C, and then D is a nice one. Y equals natural log of the square root of x squared minus 1. Right, you can be super sharp here, hopefully. Right, we know we can't deal with the square root, we've got to write it in index form. Now you might be tempted to think that this is an embedded function of the natural log. And you could go down that path, but it's quite messy, or more work than if you remember from your AS laws of logs that I can now write that the power drops down to become the coefficient part. Okay, so that's moving that from there. Ln x to the n is the same as n ln x. That's from your AS work. Okay, so that makes life a bit easier now. It's a less complicated embedded function. So it's not a product. There's no function of x times a function of x. So it's just chain rule. So dy dx will be a half 1 over what you covered up times the differential of what you covered up, which is 2x. 2's cancel, and you're left with x over x squared minus 1. And then the final example that we practice together, y equals ln x over x squared. It's a fraction, so we can use the quotient rule. We let u equal ln x, v equal x squared, du dx 1 over x, dv dx 2x. Quotient rule, dy dx v du dx minus u dv dx all over v squared. So for us, v du dx will be x squared times 1 over x minus u times dv dx 2x. Be careful when you're dealing with this now. Remember that that 2x isn't embedded inside that ln x. So I've put the brackets on there to make sure that we don't slip up there. And then that's all over v, which is x squared squared. So that will cancel with that. So we get x minus 2x ln x all over x to the 4. I can take the x out of the numerator. That x will cancel with one of the x's in the denominator, leaving you 1 minus 2 ln x over x cubed. Or you could write it x to the minus 3, 1 minus 2 ln x. And as I said in the previous clip, it's often worth, if it's not show that, and you're just working through an exercise in the book, have a look at what you're aiming for. So those are some work examples there. When it comes to the exercise, these aren't as difficult as some of the questions on the exponential exercise. So I suggest you at least do every other, but the more of these calculus questions you try, the better, the more practice you'll be, because the more obstacles you'll come up with and work your way around, either yourself or by taking a look at how I solved that. Okay, so that's differentiation of natural log.